What specific problem does the Solaris model aim to solve in the context of solar atmospheric research, and what gap in the current methodologies does it address?
The Solaris model aims to solve the problem of accurately forecasting the Sun's atmosphere, particularly in predicting solar dynamics and phenomena such as solar flares and solar winds, which can significantly impact Earth. Current methodologies primarily focus on specialized models for specific tasks, such as convolutional neural networks for solar flare classification or recurrent neural networks for solar parameter forecasting, leaving a gap in the use of foundation models that can generalize across various solar atmospheric processes. Solaris addresses this gap by being a foundation model that can be pre-trained on diverse data types from the Sun's atmosphere, allowing it to develop a comprehensive understanding of fundamental processes and improve performance across multiple downstream tasks. Additionally, it leverages a large data set covering a complete solar cycle, which is crucial for capturing the full range of solar activity, thus enhancing its forecasting capabilities. By doing so, Solaris not only improves the accuracy of predictions, but also demonstrates the potential to adapt quickly to new tasks, particularly in scenarios with uneven data availability across different wavelengths.
How does the Solaris model work? Illustrate its methodology step by step, including the roles of the encoder, processor, and decoder, as well as data normalization techniques.
The Solaris model operates through a structured methodology comprising three main components: the encoder, processor, and decoder. First, the encoder takes multi-wavelength solar imagery and processes it into a standardized 3D representation of the Sun's atmosphere. This involves patch embedding, wavelength aggregation using a perceiver-based module, and spatial and temporal encoding through Fourier encoding, which captures both fine and coarse patterns. Next, the processor employs a 3D SWIN transformer U-net to evolve this representation over time, effectively capturing the complex dynamics of the solar atmosphere. Finally, the decoder reconstructs the evolved representation back into forecasts for specified wavelengths, ensuring that the output maintains consistency with the input structure. To enhance model performance, data normalization techniques are applied, including scaling pixel values to a comparable range across wavelengths, and a transformation that balances sensitivity to both high and low intensity features, ensuring effective learning across the diverse intensity scales present in solar imagery.
Can you provide a simple yet illustrative example that demonstrates how the Solaris model processes and forecasts the solar atmospheric states, detailing key algorithm steps?
The Solaris model processes and forecasts solar atmospheric states through a structured pipeline involving several key algorithm steps. First, it ingests multi-wavelength solar imagery, where each image is divided into patches and embedded into vectors, creating a standardized 3D representation of the Sun's atmosphere. Next, a 3D SWIN transformer U-net processes this representation, capturing complex dynamics over time through local self-attention operations. The model then decodes the evolved representation back into full-resolution images for specified wavelengths, effectively predicting future states based on historical observations. For instance, when forecasting the solar atmosphere 12 hours ahead, Solaris uses two historical states at 8 wavelengths, applying normalization and transformation techniques to ensure balanced sensitivity across varying intensity scales, ultimately producing accurate predictions for both observable and emerging regions of the Sun.
What are the theoretical or practical advantages of employing the Solaris model over traditional solar flare classification and forecasting methods?
The Solaris model offers several theoretical and practical advantages over traditional solar flare classification and forecasting methods. Firstly, Solaris is a foundation model that integrates a wide range of solar atmospheric phenomena, allowing it to develop a comprehensive understanding of fundamental processes, unlike specialized models that focus on specific tasks. This broad training enables Solaris to be fine-tuned for various downstream tasks, potentially enhancing performance across different applications. Additionally, Solaris utilizes a sophisticated architecture that includes a perceiver-based encoder and a vision transformer processor, which effectively captures complex dynamics and multi-scale interactions in the Sun's atmosphere. Finally, the model's ability to leverage diverse data types and its pre-training on extensive datasets allow it to generalize better across varying solar activity levels, making it more robust in forecasting solar events compared to traditional methods that often rely on limited or task-specific data.
Describe the validation process used in the paper for the Solaris model, including the datasets utilized, metrics assessed, and how the effectiveness of the model was demonstrated.
The validation process for the Solaris model involved a chronological split of the dataset into 3 distinct parts. The training set covered data from July 1, 2010 to December 31, 2022. The validation set spanned January 1, 2023 to June 30, 2023, and the test set included data from July 1, 2023 to December 31, 2023. This temporal division ensured that the model was evaluated on future data, simulating real-world forecasting conditions. The primary metric assessed was the root mean square error, RMSE, which was used to evaluate the model's forecasting accuracy across all 8 wavelengths. The effectiveness of Solaris was demonstrated by its ability to accurately predict high-intensity regions in both currently observable areas and emerging sections of the Sun's atmosphere, indicating that it developed a comprehensive internal representation of the Sun's global state. Additionally, the model's consistent performance across all wavelengths, despite their varying scales, further validated the normalization and transformation techniques employed in the training process.
What were the main results obtained with the Solaris model in terms of forecasting accuracy and operational significance in solar atmospheric dynamics? What specific challenges did the model successfully address?
The Solaris model demonstrated strong forecasting accuracy by effectively predicting the Sun's atmosphere across all 8 wavelengths, including high-intensity regions in both currently observable and emerging areas. This capability indicates that Solaris developed an internal representation of the Sun's global state, which is crucial for understanding solar dynamics. A significant operational achievement was its consistent performance across wavelengths, despite their varying intensity scales, showcasing the effectiveness of the normalization and transformation techniques employed. Additionally, Solaris successfully addressed the challenge of uneven data availability, particularly for the 1700A wavelength, by leveraging knowledge from well-represented wavelengths to enhance forecasting accuracy for this sparsely observed wavelength. The model's ability to outperform a task-specific model trained from scratch in just 25 fine-tuning steps further highlights its adaptability and efficiency in handling data limitations in solar physics research.